very much. I'd like to start by thanking you all for being here and most importantly thanking the organizers for the invitation. It's a great pleasure and a great honor to be here at this kickoff workshop, especially as I've heard about the Malinka project I think about 1 year ago by from Carlos Simpson, and I'm delighted to see that the ERC rightfully funded this project, because as you'll see later in the talk, I think it's really important for the future of mathematics itself. So my name is Amaury Hayat. I'm a professor at École des Ponts and a scholar of the Korean Institute for Advanced Studies. But most importantly, I'm a mathematician, and therefore, a few years ago, I started asking myself this question: how can artificial intelligence help mathematicians? So to start, I'd like to take a step back and look at the world, how it was, look at the world just 5 years ago. So just 5 years ago, we didn't have ChatGPT, Midjourney, all these names that we hear so much about today. But nevertheless, most people were using AI tools on a daily basis. It's just that most people either didn't realize it or didn't think of it. And so if you're in this room, I imagine that most of you were aware of it at the time. But what we've been seeing since 2022 is essentially a social revolution based on scientific technologies, where now a large part of the general public is using AI tools willingly. So we went from a computer scientist awareness. Computer scientists have known for a long time that there was something going on with artificial intelligence since decades, to a global awareness. And in this global awareness, I include the scientists from other fields. Why? Because today we are in a situation where the youngest Nobel laureate in chemistry ever is primarily a computer scientist. So I think it's the clear proof that machine learning and artificial intelligence are changing the practice of science. And so it's a natural question to wonder, how is it going to change the practice of mathematics, and in particular, how it can help mathematicians. So maybe several of you were wondering the same thing a few years ago, at least in my surroundings, in my department. Asking this kind of question to a math department 6 years ago was really crazy. But now this idea is starting taking roots. And I think that when most mathematicians who don't necessarily know things about AI try to see if there is something that these AIs could do, they usually start to ask a math question to a large language model, or to ask it to prove a small lemma. And if you were to try this in 2022, 2023, you would essentially get terrible answers that wouldn't even make sense most of the time. But the models are evolving quickly, and if you start again today, you might see that from time to time you actually get something that is useful, or at least definitely makes sense. Up to the point that 6 months ago, at least a little more than 6 months ago, for the first time of my life, I tried to ask O3 at the time to prove a small lemma that I would use in a paper. The kind of lemma that takes you 1 hour and a half to prove, and that's not very hard. But in 35 seconds, I had the proof, and the proof was correct. So we are at the stage where several peoples are now claiming that GPT-5 could solve open problems on its own and give open proof of open problems on their own. I think there is some precaution to take with these kind of claims, and in particular of the post in here, but at least it shows that the debate has started. And because of this kind of debate, in the last few months with two students, Antoine Perronnet and Fabien Glöckle, we decided to create a live benchmark of lemma that are extracted from the latest archive papers. So essentially, you take papers that are just released this week on archive, you extract the lemma, and you make sure that you read the paper to have all the assumptions on the lemma to make them self-contained. And then you ask language models to prove them, and you see how well they perform. Well, if you do this, what you can see, this paper was submitted a few days ago, but will probably be on archive soon. What you can see is that these models essentially get 10% accuracy. So it means two things. First, they are still really far from human mathematicians, because being able to prove 10% of the lemma is far from a professional mathematician. But the performance is not zero. And 10% means that in some cases it was as good as mathematicians who are actually releasing papers on archive. So there are many other things that you can do with generic LLM, but this is definitely not the type of thing I want to talk about today, because what I'm going to try to convince you is that AI for mathematics is much deeper than using generic LLMs. Yes?
In this benchmark, how do you do the formalization of the statement?
So in this benchmark, there's no formalization. It's purely natural language. So then you're going to ask the next question, which is how do you evaluate? So that's what is hidden in the human confidence score. We use another LLM to judge whether it's correct, and then we had the humans reviewing the proof by hand to try to see how we can trust this judge. And you can see the different judges, they have a confidence score that is very far from 100, but above 80%. So this is just supposed to give a proxy of yes?
But sorry, do you also weight the difficulty of each lemma? So this is like a weighted thing, or?
No, we didn't weight the difficulty of the lemma, but we restricted to lemma, to the things that are between essentially to lemmas only, no proposition and theorem, precisely to have something easier.
Okay,
sometimes lemmas are more difficult.
Yeah, sometimes, yes, of course,
Yeah,
of course. But this is always an average thing, you know. So.
I was just wondering if the 12% were the lemmas that are trivial, so if there was a...
Yeah, there are some parts. So a good follow-up question will be how many of these lemma were trivial. Usually the proof that were given are about 1.5 page long. So.
Excuse me,
Yep.
just from the explanation, but the data set is fixed or you extract every week?
So, I mean, this is the first week, so I can answer your question in 1 week.
Okay.
So,
And this is top 5 or I don't know, how do you test exactly? Like usually sometimes you do best of 5 or...
no, right now it's pass at 1. So best of 1. So indeed, it's, you could do best of 120 SE. Yeah, that's definitely something that could be done then later on. The goal was really here just to give a proxy because, as we'll see later, because it's not formal mathematics, it's nice to try to have an idea of what large language models can do, but it's not going to solve the fact that if you want to actually do mathematics, you need something that guarantees the answer is correct. So thanks for these very good questions. And after this very long introduction, my talk will be essentially in 2 parts. First, I'm going to try to convince you that outside proving, AI is already useful as a tool for math discovery, for discovery in mathematics, and has been in the last few years. And in the second part, I'm going to talk about theorem proving again, but this time in a formal language. Usually I try to introduce this part as will AI prove theorems on its own, but I think that the more honest question nowadays is more when will AI prove theorems on its own, because I think it's more a when question than an if question. Although if you disagree, I'll be very happy to discuss that at the end of the talk. All right, so let's start with the first part, AI as a tool for math discovery. And I'll start by saying that solving math with a computer is not something new. And those who know me know that my favorite example is this one. It's a conjecture from Euler of 1769. So of course they didn't have a computer at the time, and what Euler thought was true is the following. If there exist k plus 1 integers such that, I'm gonna, k plus 1 integers so that if you take the k first one, put them to the power n, and they're equal to the last one to the power n, then k has to be larger or equal than n. I forgot the fact that n I think has to be larger or equal than 2 or something like this. So this Euler wasn't able to prove this during his life, and this remained an open problem for almost 200 years. No mathematician was either able to prove it or to disprove it. This is until Lender and Parkin arrived in 1966, and they solved this problem in the most silly way you can think of. They tried many combinations with a computer, and they got this, right? So if you look at this, here you get essentially 4 integers to the power 5, and it's equal to a last one to the power 5. So if we go back to Euler's conjecture, it will mean that 4 is larger than 5. We all know that this is not correct, so this was a new mathematical result. But most importantly, it's also the only math paper that I know of that can fit on a single slide. Right? So since then, there were other examples, maybe more serious examples, or at least more involved examples. For instance, the proof of the last remaining case of the Kellos conjecture in 2019. I'm not going to try to get into the detail of what this problem was, especially because I think there are people who are much more expert than I am in this problem in the room. But essentially, it can be reduced to a proof with many simple cases to check. The only problem is that these simple cases are far, far too many for a human. And because they are far, far too many for a human, these researchers use a computer to solve it. And I think you can realize how hard this would have been for a human by looking at how long is the proof. In fact, you're not even asking how long is the proof in number of pages, but what's the weight of the proof, and the answer is about 200 gigabytes, which is about 10 times Wikipedia. So if you want to read the proof and check it, by hand and without any computation system, you're never going to make it. It will be an interesting question to see if all the mathematicians on Earth were to do this, could they do it by the end of their life or not? All right, so the conclusion of this is that computers have been used to prove theorems for a long time. But in these cases, essentially, the problems were abstractly, essentially a high number of case checking. Now that we have very powerful technologies in machine learning and in artificial intelligence, can we use this to solve more complicated problems? So I'm going to try to convince you that the answer is yes, but before detailing one example, I'm going to try to summarize a bit here what the hope is. And the hope is that for many problems in mathematics, we rely on an intuition. Sometimes you don't have a theorem that shows a question to solve a problem, and so you have to think about what you're going to do next. And this intuition is an important concept in mathematics, and in a number of cases, maybe not in all problems, but in a number of open problems, it resembles a kind of pattern matching. So you've seen plenty of examples, and it gives you an idea of how to proceed in a case that you've never seen before. But the thing is, we know that neural networks are very good at pattern matching. So the natural question is, can we train an AI to have a better mathematical intuition than us on specific problems? And the answer that I'm going to try to convince you that the answer is yes. And this is something that we try to do on several examples. And I'm here going to try to present one example from one field of mathematics, which is the stability of dynamical systems. So let's start, and let's take a dynamical system. So you have x prime is equal to f of x. Okay, x is a vector of n dimensions. So we have n coordinate. F is C1. And you assume that f of 0 is 0, meaning that 0 is an equilibrium. Right? So if you start at 0, you remain at 0, because x prime of f of 0 is equal to 0. And the question you'd like to answer is the following. Is this system stable? So stable means that what you'd like to answer is it true that for every epsilon, there exists a delta such that if the initial condition is smaller than delta in norm, then not only the solution exists for any time, which is not granted for nonlinear systems, but in addition, it always remains smaller than epsilon in norm. So in other words, are all solutions arbitrarily bounded if the initial condition is sufficiently small? So if I make a drawing, it looks like this. For any red ball, can I find a blue ball such that if I start in the blue ball, well, I'm not sure what my solution is going to do, but at least I know it's not going to exit the red ball. And if you can answer yes to this question, you have proved that your system is stable. So this is a problem that has been studied for a long time. One can think, for instance, of the work of Henri Poincaré with the free-body problem. I think it's the right place to mention this name. So it has interested mathematicians for over 100 years. And thanks to Netflix and News Engine, it has also interested the general public for about 3 weeks last year. I don't know if you've seen the three-body problem, the Netflix TV show that essentially sparked it online for about 3 weeks. All right, so in this problem, there was a significant advancement at the turn of the 20th century with the so-called Lyapunov functions. So what Lyapunov showed is the following. When you try to solve this relatively hard problem, that is the stability question, the answer is yes if you can find a function that is strictly minimum in 0, that goes to infinity at infinity, and satisfies this weird condition between the gradient and the dynamic, which essentially means that it's a sort of energy in the system. Essentially, if you have an energy in the system that decreases, then your system is stable. So this is an extremely powerful result because it reduces a very hard problem to finding this kind of Lyapunov function. The only problem, there's just a tiny little detail missing, and this tiny little detail is that nothing tells you how to find a Lyapunov function. And in fact, this is not really a detail. This is actually a hard problem. For instance, if I give you this system, and I would like you to tell me whether there exists such kind of decreasing energy, well, you could spend some time on it, even though it's a very easy example, because if I give you the energy, or one of the energies that are behind, you see that there is no cross term between x1, x2, and x3. It's a purely simple polynomial. So even in this easy example, it's not super easy for mathematicians to find one. In fact, it's such a hard problem that today we're in a situation where you can have a very nice paper. I think this paper is cited more than 100 times, where you show that this class of system or this class of system have or doesn't have a Lyapunov function. So today, more than 100 years later, it's still an open question. We still have no clue whether this question could ever be solved in a systematic way. But one thing is clear is that there is no systematic way to construct a Lyapunov function. So what do we do in these cases when we are a mathematician? Well, we resort to intuition. And so precisely, this is something that we try to do in AI. We try to train an AI to have a better mathematical intuition than us at finding these kind of energies in the system. So this is something we did with Alberto Alfarano and François Charton. Alberto Alfarano is at Meta AI and François Charton is at Axiom, a company in the US. And the way we proceeded is the following. You first train a transformer, so the same type of thing you have in ChatGPT but in smaller. And you do as follows. You generate a set of system and associated Lyapunov functions. So you need a lot of examples, a system and the energy, the decreasing energy that you like to have as a solution. You create a lot of them. Then you encode the example in something that the neural network can read, essentially, and then you train in a supervised learning. There's nothing fancy about that. The hard problem really is the first one. How do you generate that many examples? Why is it a hard problem? Well, how do you generate problems and solutions for a problem that precisely you don't know how to solve, right? So the way we did is the following, because it's the only way we can do. Instead of sampling a problem, then trying to find a solution, well, we created what is going to be the solution, and then we create a problem such that this is the solution, right? So of course, so in this situation, it means that you want a mathematical way to have a function that is positive and goes to infinity at infinity. And then you're going to create a system such that this is an energy for the system. So in spirit, you're using the fact that one direction of the problem is easier than the other. And precisely, the direction that is easier is the one that you're going to use to create your data. And the other one is the one you'd like to solve. So, of course, if you're doing this, even if you have a perfect generator that can generate all the possible stable systems in the world, this will bias your distribution. And it means that you need to be very careful once you train your model to make sure that what you trained makes sense and that if you test it on something completely different, for instance, problems that you will find in textbook, it actually finds the solution. Because otherwise, it means that you have learned the generator and you haven't learned the math behind. And while learning the generator might be an interesting experiment, it's absolutely not what you want to do when you want to learn mathematics with an AI. All right, so okay, the rest is relatively easy. You can always relatively easily encode a mathematical expression in a list of tokens that the transformer can read. So if you're doing this, well, it's going to work. And this is what happened. The AI learned the mathematical intuition of a Lyapunov function. It works, in fact, exceptionally well if in the training set you put a few high-quality examples. So a few examples that look like the type of thing you will have in textbooks. So not only artificial data, but like human data. It helps realizing that there will be different distributions. And in fact, even, this was a surprise to me at least, that even 50 examples out of 1 million in the training set make a difference. So at first I thought this was a glitch, and then my co-author showed me that the improvement by adding high-quality examples was continuous from 50 examples to 5,000. So then it's harder to believe in a glitch. So if you do this, this is the kind of results that you obtain. And first of all, I need to apologize. I told you that there is no systematic way to find a Lyapunov function. In fact, there are specific classes of system where there is. One of them, I mean the most famous of them, are the systems that are written that are polynomial and that have a sum of a Lyapunov function, so an energy, that is a polynomial written as a sum of square. In this situation, you have algorithms. In theory, they work all the time, more or less. But in practice, they can be quickly costly in memory and in computation time. So it depends what is your threshold, what are the limits of your computing capacities. So this is why here, when we tried these algorithms, they don't get 100%. And so you see that the AI model not only gets very high numbers on polynomial systems, but also the last line are non-polynomial systems. And you see the AI has very high numbers. Yes?
Sorry, just a question about what you said. Are you allowing the same amount of computing time for the SOS algorithm as you allow for all the training of the entire system?
Not for the entire training, but once the system is trained once, it's not trained per system. Once you've trained the full the neural network once, you can test on any system as you want. And then in the inference, we allowed 1 hour. Of course, it's CPU versus GPU, so it's hard to compare. But we allow 1 hour or 1 hour and 30 minutes for the sum of square, and we allow, I think, 5 minutes for the GPU inference time. Yes.
Have you done the same test for high thinking models like GPU?
Oh, yes. I mean, we tried for fun, but we don't have the numbers. I mean, I'd be surprised you get above 10%. I mean, we can. This was before GPT-5. This was at the time of 04 Mini, and so we can try with GPT-5. That could be interesting. The difference is that here, I mean, to defend a bit these reasoning models, here we're not asking for a proof. We're asking for an energy, and then the human mathematicians check that it works or not. So it's a slightly easier problem than.
It's like a fine-tuning problem, right?
Yeah. Yes, it's like a fine-tuning problem. The thing is, if you start to try to fine-tune then on a large language model, you will need an amount of data to get something correct that is huge, while here, I mean...
The challenge is that with low-rank approximations, this is usually, it can be sometimes done with very small data sets.
Yeah, sometimes it can be done with very small data set, but here you're really trying to get a pattern that is really far from being obvious. So essentially learning the language, okay, I'll say it differently, learning the language behind is not necessarily useful to solve this problem. So in this regards, it's probably easier to train a small model. Yeah, a 100 million parameters model will make it. So there's no need to go to a 1 billion, I'd say, or even less to 100 billion. All right, so these are relatively high numbers. Now you might wonder, why do I say these are relatively high numbers? Well, to be convinced, I tried on my class of master students in my course of control theory at Institut Polytechnique Paris, not very far from here, and I got around 10%. And then I decided to try on myself to see, how it's compared. And I got 25%. So this is just to say that if you have someone who believes that they will be better than the AI in this thing, I would be very happy to organize a duel. Just let me know. All right. So so this article was featured in the New Scientist. I put this slide because the funny part of it was that because there's a paywall, it took me 1 week to understand what they wrote about us. Maybe more interestingly, there was a Japanese YouTuber who did a video about this paper. So I don't really know what's in the video. I've heard that this story of a fisherman who teaches his granddaughter what a Lyapunov function is. There's only one thing that is clear, is that this behind is our paper. But right, there are subtitles, but they are in Japanese. So if you speak Japanese, you can let me know what's inside. Yeah, right. You're right. Should probably do this. Oops, sorry. All right, so if I summarize the paradigm of this approach, what you're trying to do here, from an AI point of view, is not very complicated. You're trying to train a transformer to have a mathematical intuition on the problem. The hard part is really to have a generator of data that is meaningful from a mathematical point of view, right? To generate the data in a backward fashion in a way that is sufficiently generic to allow the model to generalize outside of distribution. Now, the second key point is to test on out-of-distribution examples, ideally something you'll take from textbooks, but otherwise things that at least are generated differently, to make sure that you actually learn the math behind and you're not learning the generator. And this architecture and this framework, this pipeline, have been actually used in many frameworks since then. It's been used to find explicit solutions to ODE. This was, I think, the first use, then to local controllability of systems, many different ones. And if you want to try it yourself, you can. So this is the link of the repo. It's normally relatively easy to modify. There's a tutorial on it. But if you have any question, you can also ask me. I'll be very happy to answer this. Yeah. I see some people noting, so then I'm going to wait for.
Can I ask you,
Yeah.
can I ask another question?
Yes.
Well, what about if you try to use your diagram that you showed at the start of the picture?
Yeah.
So you try to take your equation.
Yeah.
Choose some kind of equation sort of, and try to take your equation and see if it looks like it'll be stable by plotting the
Yep.
vectors.
So there were approaches doing this. There were.
It looks like it should be stable. Then you look for the other one.
Yeah. This, I think, will be a very good way to try to select the data. So the one challenge right now is that if you generate a system at random, most of the time it's not stable. Actually, with this, we were able to realize that there were many more that are stable than I expected. For small systems, you can get up to 8% or something like this. But it's still not much. So indeed, there are people who tried to know whether this was stable or not, and even to try to design a Lyapunov function that will be itself the neural network by essentially every time you have something that doesn't work, you try to put it back and so on. So the drawback is that you retrain your neural network for each system, but on the other hand, you have something that is perfectly tailored for your system. So there's a high hope that it works. Right now, all the examples that I've seen haven't been so convincing, but I really believe this is one very natural way that should end up being the one that works the best for a very complicated system. Yeah, so there were several approaches like these. Yeah.
But I was just meaning to generate examples on which you
Ah.
can apply your...
Oh yes, but when we generate the examples and to train, this is a supervised training, so we need the solution as well.
No, I mean generate the testing.
Ah, yeah, okay, yes, that will be a very good. That will be a very good. Actually, to generate the test examples, we were doing something a bit like this, but not as clever, and so something extremely costly as well. We generate at random. We do a lot of tests, and then we discard all those that doesn't work. So we discard 97% of the systems. So this is the reason why we can't use this to generate a training data set, because it takes already a lot of time to generate just 1,000 to test or 10,000. So imagine generating 1 million examples like this. Yeah. So yes, indeed, that's a very good idea. All right, so there were subsequent approaches, slightly more complicated, but also very useful. This one is called the pattern boost. It was made by François Charton, Jordan Ellenberg, Adam Wagner, and Jordi Williamson last year. The goal is not only to train a transformer to get the intuition, but to use it to improve a classical techniques that is known. So you'd like to construct objects in mathematics that are interesting with respect to some metric or to some criterion that you're setting up. You have ways to construct these kinds of objects. For instance, you'd like to construct a graph that is the widest possible with the lowest number of edges or something like this, or this is a silly one. You can get actually meaningful ones. And the way you do is the following. First, you generate a lot of examples with a classical method, the one that you know. You filter out the best. You train your transformer on this best. Then you use the transformer as seeds for your classical algorithm. Then you generate a lot of examples, you filter out the best, and so on and so on and so on. And the hope is that they will both get better and better at each iteration. And they show that in a few examples they did got better, and in particular in graph theory they were able to close a conjecture that was 30 years old by creating a counter example to a conjecture of 1992. All right, so there are many other examples with this kind of approach. You try to learn the mathematical intuition behind the problem and then to suggest the solution to the mathematicians. There were examples in topology. There were examples in group theory, and I saw that Alexander Shervov is in the room, so so you can ask him if you have questions. There were examples in partial differential equations. You might have seen this. There were newspaper articles and an archive paper last week from a team between DeepMind and several mathematicians co-led by Javier Gomez Serrano, who are trying to find the answer to the millennium problem about the Navier-Stokes equation, so no less, and in many other fields. Right, so I hope I convinced you that AI is already useful as a tool for math discovery. We organized a workshop last week in Oberwolfach, and apparently some people found during this week a new formula in representation theory that seems to be important for something. I must admit that I didn't get why or what it was, but apparently people were happy. So just to say that, yeah, I hope I convinced you that it is already useful, and that this augmented intuition will allow us to bypass the difficulty of the problem, and it's particularly well adapted to the problems where you can use this kind of augmented intuition that bypass the difficulty, because checking the solution is easier. If you have a problem where checking the solution is as hard as finding it, then it's going to get a bit harder to apply. Now, in all these examples, the AI is only a tool. The humans is still doing the reasoning. So we could wonder, can an AI prove a mathematical result on its own? And I think, given the topic of the workshop, it's the reason why we are all here in for these 3 days. And so this is my second part. I'll start by saying that for me, of course, this is a much harder problem, having an AI to prove mathematical statements. For me, this is also a shocking question. As a mathematician, it really calls into question our very vision of mathematics, at least my vision of mathematics. And when I started, I thought that this was a science fiction future that was probably only 20 to 30 years away. I wouldn't bet on 20 years today. I think it's probably much closer than we imagine. Much closer. So if I were to ask you, can you design an AI that can prove a theorem? I'm pretty sure the first thing you will try to do is create a GPT model, right? So you have a GPT model, you give it a question, then it goes in a GPT model, and then you hope that it will output a correct proof. Classic LLM. Now, to understand a little bit more how we could design this, especially for mathematics, we need to get inside what happens in the GPT model. And this is what two people did in 2020. I think this is the first work I've seen with kind of large language model in formal mathematics, to prove theorems in formal mathematics. This was done by Stanislas Paulu and Ilya Sutskever. Ilya Sutskever is a scientist who is mostly known by the general public for being the person who told Sam Altman, the CEO of OpenAI, that he was fired, and then getting fired afterward. But he should be known for something else. He should be known for being a very impressive researcher in AI, and citations and H-index doesn't really make a good representation of scientists, I believe, but they might, they might be a proxy to something. And when you see his profile, knowing that he's about 40 years old, you can know that he was there not only for one revolution in AI, but several. So just to say that, in the AI community, this kind of problem interested very senior people already in 2020. So to understand a little bit more how we can design this for mathematics, we need to go in 20 seconds in detail of how works a pre-trained transformer, an autoregressive transformer. So let's imagine that you have something similar to what's inside ChatGPT, much more simplified. So we're only looking at the autoregressive transformer part. Let's imagine that you have a network that is trained to complete a sentence. So you will give it a sentence. It will take your sentence. Then, thanks to the training, it will compute a density of probability of the next token. Let's assume this is the next word. It will sample thanks to this density of probability and get the next word, and then put it back. The autoregressive part is to put back in the sentence and to do this again. And because this sentence, hope is a good thing, maybe the best of thing, and no good things ever dies, is a quote from the movie The Shawshank Redemption, which is #1 on IMDb, I think. So if you haven't seen it, you should really see it. The more your sentence is going to look like this quote, the more, if you train on the internet, your density of probability is going to be spiked on the next word of this quote. And so at the end of the day, you have something that your network is going to sample a token that means end of the sentence, and it will return your sentence. So you might think that, okay, let's do this for mathematics. So we have a statement. We compute the density of probability of the next theorem to apply, for instance, or the next step of the proof. We sample a next step of the proof. We put it back in the sentence, and we do this again, and at the end of the day, we have something that says this is the end of the proof. And if it worked correctly, you take the right column, and your right column is the proof. Now, doing this is a bit naive at first, so there's a slightly better way of doing it. It's when you have, if you work in a formal language, and so you have a computer assistant, what you can do is have your statement, compute the density of probability of the first step to apply, or the first tactic to apply, and then you apply this to the statement. So for instance, this is written in Lean. You have this statement to show. You apply this theorem, and now this is the state of what you have to do. So this is what you have to show. So you have the two assumptions of the theorem to show. And so if you're doing this, and you keep applying theorems, if it works at the end of the day, you don't need a network to tell you there's nothing to prove. At the end of the day, you will literally have nothing left to prove in your computer assistant, right? So this is the slightly more advanced way of doing. And this is what was done by Stanislas Paulu and Ilya Sutskever in 2020. The hope in this is that by seeing enough examples, the AI will be able to learn how to reason by itself, or at least to learn how to prove theorems by itself, by predicting the next step each time. And you might think that this is overly optimistic, because just predicting one step at a time is a bit short-sighted. But on the other hand, ChatGPT is able to write relatively nice essays, and they learn the next word. I mean, not even the next word, the next token every time. In any cases, whether you're optimistic or pessimistic, this can only work if you have enough examples. And enough mean sufficiently diverse and sufficiently numerous. And this is a big limitation because in mathematics, we really lack data. We lack data. We have very few data available. In particular, we have very few formal data available. As you know, and this is really the object of these days, you have two ways of writing mathematics. You can write mathematics in an informal language, in a natural language, so French, English, and you can write mathematics in a formal language. So the formal language here is on the right, and the main thing is that we have a lot of data in informal language, in natural language, but we really don't have that many in formal language. So here I'm still taking the example of Lean. I think there will be more examples in Rock. But in Lean, for instance, you have around 300,000, maybe 400,000 theorems by now. This is a large data set for a human. I mean, I'll never know 1% of it. But for an AI, to train an AI in a supervised learning like a large language model, or even to fine-tune a large language model, that's not much. So this is the limit of the approach. And so what can you do? What can you do to tackle this limit? Well, the very first thing you can do is try to change the process and to optimize the process on the way. So instead of having just a large language model, you're going to try to train a retriever at the same time, so something that can read in a math library and get some important theorem and then suggest the theorem to the large language models. Another thing you can do is to try to fine-tune the best large language model you can find with very high quality data. So there's a very nice paper from Fabian Glöckle of 2023 who is essentially showing you what you can do, but also what you can't do with this kind of approach. So what are the limits? Once you've done this, you can try to tackle the lack of data. So you can try to first gather all the data you can from the internet, right? So this is not necessarily a trivial task, but you can try to have all the possible data in Rock, for instance, you can find on the internet. Then you can try to create your own data if you still don't have enough data. So you can try to have synthetic generator of data. So this is what we did with the hypertree proof search. You can start by a statement, apply many rules, and see what it gives at the end. And this gives you a completely artificial and probably completely meaningless theorem. But at least these are some data you can use to train. Or you can try to have an automatic formalization. You can try to make sure that you have something that translates from natural language to formal language to try to have more meaningful formal language data. And so doing this essentially means that you will have more formal and verifiable data. This is by far not a trivial task, otherwise I guess we wouldn't be here today. Because, as you know, when humans are writing proofs, they are skipping a lot of steps. And in this sense, human proofs cannot really be considered as self-contained, at least not in this regard. So it's a non-trivial task to be able to switch from one to the other, especially because it requires a kind of proving to fill in the gaps left by the humans. I'd like to emphasize that auto-formalization, as it is seen right now in the computer science community, is really seen as a means toward having more data to train AI models. But from a mathematician point of view, this is really also an end. Because imagine you have this kind of tool, this kind of a dream tool. You can have someone putting a paper on archive, and then instantly you have something that creates the whole proof in a formal language and tells you at least whether the proof is correct or not. And this would allow to check the correctness of new mathematical theories. And if you believe that there is no need for this tool and that humans are already doing a good job at checking the proof, but I see some people smiling, so I guess no one believes that. I'll be interested to know how many papers you review per year, and also I have some counterexamples. There is these famous two papers, unfortunately famous two papers. So these two papers were published in Annals of Mathematics, likely the most prestigious journal for pure mathematics, and they strictly contradict each other. So they can't be both true at the same time, right? So they're like, apparently, there was one which got retracted, I think, only 2 years ago. So you see, they're older than that. They're older than that. And I personally still don't know which one was correct. Playing the stat, I will bet on the second one because the second one knew that the first one existed. But so you see, this is really a problem even for very strong mathematicians. Now, auto-formalization is a field that is improving extremely quickly. At the beginning of 2024, people were essentially able to have very good statement auto-formalization for a very specific type of exercise or problems, namely problems that looks like Olympiad from high school level, international mathematical Olympiads. So you see, these are, from a mathematician point of view, this is relatively restricted. In 2025, in June 2025, we were told that, from a team of deep minds, that it was possible to auto-formalize 4% of the statements in archive. If you think about it, 4% of the statements in archive is a lot. It's a lot of statements. A few weeks later, it was revealed that for the first time there was an archive paper that was completely auto-formalized, not directly from the paper, but from an extended version of the paper. So essentially the original paper was 6 pages, I think, and the second version was 30 pages. But still, from this point, it was auto-formalized with very little human intervention. And there was a second paper relatively recently by Mathematicians, which is essentially a branch of the same company. So there are still a lot of challenges. It's still a very hard problem that is extremely far from being solved, hopefully less than 5 years from being solved. And but it's something that really is going very quickly. So I think it's one of the hot topics of the time. So let's go back to my limit in the data. So you can improve the process, gather more data, create more data, auto-formalize more data. Well, at the end of the day, if your goal is to prove automatically at the level of a human, it might be that this is not completely enough. Why? Well, imagine that you want to prove things in a very specialized area of mathematics, and this is the case of most, or at least a large number of mathematical subjects in research. Then, by definition, you are in a low data regime. You can auto-formalize all the data that are on archive. By definition, there are not that many. A lot for a human, but probably not a lot for a machine. So how can you go further? Well, one way to go further is to treat mathematics as a game. So essentially to use reinforcement learning. So this is something we started doing in 2022 with Guillaume Lample, Marianne Lachaud, Thibault Lavril, Xavier Martinet, Gabriel Ebner, Aurélien Rodriguez, and Timothée Lacroix. I'm spelling out all the names just to show that it's something we worked for 2 years and a half, and most of them were at full time on this problem. And the motivation was really looking at the papers from DeepMind, where I think you've all heard about AlphaZero. You have an AI that is trained to play chess against itself, and after 3-4 days of training, it's better than any human on Earth. So we thought, let's do the same. Let's train an AI for math, and after 3-4 days, we can all enjoy having a glass in vacation, and so what's the game? What's this math game? Well, the math game is the following. So you want to prove something in a formal language, so you prove things in the backward fashion. So you have a statement to show. You make a move. So making a move is applying a theorem up here. Once you apply the theorem, now you have to show the assumptions. So you have 2 things to show. You make a move. You have nothing left to show because this theorem has no assumption. Here you make a move. You have 2 things to show. You make a move, nothing, and you make a move, nothing to show. And if at the end of the day you have nothing to show, well, you won. Right? So if you try to do this, then there will be several non-negligible difficulties. And the main difficulties are these ones. You have 2 types of difficulties. You have mathematical difficulties. So starting from the end, the number of possibilities in mathematics is much, much larger than in chess. In chess, you have 100, 300 possible moves. In mathematics, you can just come up with a new claim, a new lemma, or so it's a nearly infinite number of possible moves. In mathematics, it's also extremely hard when you are in the middle of the proof to know how likely you are to succeed, right? I mean, once you've done the critical steps, then you probably know that you're likely to succeed, but it's extremely hard, and it's even harder to know this automatically with a simple criterion. In chess, you do have heuristics, right? I mean, you just count the number of points. It's not perfect, but at least it gives you something. You can do slightly better than that. You can look at the yellow. I mean, there are a few things that you can do. Then you have machine learning difficulties. The first one is that when you make a move in chess, you start with 1 chessboard. You move the rook. You still have 1 chessboard. Right? In math, you have 1 statement to prove. You make 1 move, now you have to satisfy the assumption, and now you have 2 statements to show. So it means that if you are making a lot of moves without being careful about that, you might end up with like hundreds of thousands of statements to show. And even though they will be all completely trivial, you might just explode in terms of memory. And so you might fail for a very bad reason. Not because it's hard, not because you don't have the capacities of solving it, just because you didn't implement it right. And finally, and this is really the main, I think, difficulty from a machine learning point of view, playing chess against yourself is a two-player game. So you can start with a lot of AIs that are very bad at playing chess. They're going to compete against each other. And at some point, one is going to win. And so you know that this way of playing chess is much better than this way of playing chess, or at least better. And you can use this to train, right? So of course, it's not easy, but at least you have a hope that they will get better and better and better, and this is the way your training is going to start. Now, you have a lot of AIs that know nothing about math. You ask them to prove a small exercise that you find very easy. None of the AI managed to prove this exercise, and so you have nothing to train your model, right? So this is a harder problem for this reason. It also means that you can't start with AIs that have just been initialized. You need to start with something that already has a bit of capabilities in mathematics. All right, so just to prepare you to the fact that it's much more difficult than chess, and that as of today, no one has been able to create an AI mathematician better than the actual mathematicians, fortunately. All right, so how did we do in practice? Well, in practice, to try to tackle this at least a little, we had two transformers, so two models. One that was trained on a lot of supervised data, or at least all that we could find, and then that learns how to predict the next step. Another one that tried to judge how hard a statement is going to be to show. So that if you say, I'm going to apply theorem A, and so then I'm going to have to satisfy these assumptions, the second model can tell you, wait, these assumptions, they are extremely hard to show, try something else. And by doing this, you can explore essentially the graph of possibilities. And once you have examples that succeed, you can use them to keep training your two first models, and you can go on like this. I won't detail it that much, but what we were able to do after that was essentially we essentially ended up with a model that was able to show around 60% of exercise at high school level, up to Olympiad levels, and a few exercises from the International Mathematical Olympiads in informal language. Now, and this was agnostic informal language. This was working in Roque, Isabelle, or Lean. I know there are a lot of people who focused on Lean afterward. Fortunately, there are people like Marc Lelarge who are focusing on Roque as well to have some more diversity. But at the time, it was really agnostic in terms of formal languages. Yeah. So these results are really outdated. I mean, nowadays. So yes. So this is the kind of exercise it could show. You can show that for any n, 7 never divides 2 to the power n plus 1. So I can wait a few minutes and you tell me if you have the answer. Now, if you don't have it, I can give you the answer of the AI, guaranteed correct. These results are really outdated today. I mean, today you have approaches that solves around 99% of these high school exercises. In the last summer, you had some provers that will get a gold medal at the International Mathematical Olympiads, even in formal language. But this was 2022. 2022, ChatGPT didn't even exist. The largest model we could find internally was 700 million parameters. So really, this was not very long ago from the point of view of mathematics, but like several eras ago from the point of machine learning. So to have something more modern, last year we decided to design a second version of it, which would use modern LLMs, so based on modern LLMs. And what I think is interesting about this paper is that first you can recover the previous results with 20 times less compute, which is always nice, especially when you work with academic compute. But I think most importantly, we used very, very few additional data in the training. So instead of trying to gather all the possible data that we could find on the internet, we used essentially 240 examples of exercise, while the most recent models are using 2.4 million examples of exercise. So you see they're much less, which means that the progress that were made with this kind of reinforcement learning are completely orthogonal to the most recent progress made by other provers with auto-formalized or synthetic data. Now, talking about, yes, and so every time I'm presenting this slide, I'm saying this should be open sourced soon, and we will get approval from Meta and my colleagues from Meta. But it turns out that didn't happen yet, but I was told that it will be very soon. So yeah, let's make the bet that in a month and a half this will be done. All right, so if I take a step back again, I showed you one type of reinforcement learning for theorem proving. That is the proof search, where you try to learn to predict step by step and to choose step by step. So essentially, the model is trained to predict the next step. There was another type of reinforcement learning that was developed essentially starting last year and a little bit at the end of 2023, which is the whole proof generation. And I must tell you that the first time I've seen a paper, this was from DeepSeek, which was at the time a relatively unknown company, saying our first prover in Lean used a whole proof generation. So I trained the model to generate the entire proof of the theorem, and if there is anything that is wrong, I just discard the theorem and I try again. I thought, come on, this is very bold. Like, this is never going to work, right? Turns out that the good point of doing this is that you can use a type of reinforcement learning that happens to be much cheaper in terms of training, at least with this setup. I'm not going to enter in the detail of why. It's those 4 letters, GRPO, that you might have seen several times. This is also the thing that led to DeepSeek R1 and later to the reasoning model that you've heard about, I'm sure. The thing is, in both cases, in both cases, oh yes, so what I want to emphasize here is that when you are generating the whole proof, usually you can only train on problems where you have a verifiable answer. So for DeepSeek R1, for O1 most likely, for these models, what was done is that in the training data, you have a question, and you have a lot of questions to solve, and at the end of the day, the only thing that you check is the answer. So you need problems to train where you can check the answer, and if the answer is correct, the proof is most likely correct. So you're using the answer as a proxy of the proof, and of course, from a math point of view, it reduces a lot the type of question you will get in this training set. But this is only if you work in natural language, because if you work with a formal language, then you do have your verifiable answer at the end. You're just asking your favorite computer assistant whether the proof is correct or not. So I think there's a huge interest of formal mathematics with this kind of method. And this kind of method can also be used for auto-formalization. Actually, there are many people trying to train this kind of neural network to auto-formalize theorems. So not only, you wouldn't only ask it to generate the whole proof, you would ask it to generate the whole proof from the natural language proof. Now, there is a main limit of reinforcement learning, is that it's well known that usually reinforcement learning improves, and at the end of the day, you end up having a collapse of diversity. And you try to have this collapse as late as you can. But at the end of the day, if you generate the whole proof, you're still going to get this collapse. And so to mitigate this collapse, so how can we tackle this? Well, to mitigate this kind of collapse, we introduced a new approach last week. I mean, been working on this for a long time, but this is also a paper from last week. Where instead of trying to generate the whole proof, you're going to use the same type of reinforcement learning, but you will have 2 models working together, a sketcher that's going to try to come up with a skeleton of proof with lemmas to be shown. The rationale behind is that if you take a natural language proof, it can sometimes be seen as a skeleton of proof for the formal proof. And then you have a prover that is asked to actually prove the different lemmas. The good point is that instead of generating a full proof and then discard it if it's wrong, you do the same for the lemmas, so you are discarding smaller proofs, so it costs less to discard and you have a higher probability of succeeding. And you can see here so this is an experimental curve, and you try to see the accuracy of the model on some given exercise to show with time while training. And the blue curve, so the blue curve and the orange curve that are here are the classical GPRO, the one I was talking about with the whole proof generation right before. The green curve is a variant of this one, so a variant that was introduced in 2025 to try to improve GRPO. And the red curve, the one that ends up above the other ones, is essentially this procedure. Right, so just a final slide to say that things are moving extremely quickly. In 2019, these are the type of things that a neural network could show. This is not a joke. This comes from a research paper. Nowadays, you have several models obtaining gold medal at the International Mathematical Olympiads. If you've tried recently GPT-5, Gemini 2.5 Pro, or the latest Magistral from Mistral, you've seen that these models, you've probably seen that these models have good capabilities in mathematics. Actually, they are at the point where they are good enough to convince you of things that are completely wrong. And so I think this is the reason why formal mathematics is more important than ever. But the models undeniably start to have performance that are close to humans, or at least to some humans. Okay, so I hope I convinced you this is a topic that is important for the future of mathematics. I really don't believe that AI will replace mathematicians. I think it's just that the practice of mathematics is going to change, and that's okay. It has been changing a lot in the past. I mean, if you think about it, there was a time where computing the digits of pi was essentially one of the major problems. Now this has been accelerated by a lot. And I thank you for your attention.
Okay, so questions?
You've been concentrating on proving, but if
Yes.
you look at what we as mathematicians do all day, I mean, there's three things we do, right? We conjecture,
Yep.
we prove, and then I think a very important thing that's kind of like your intuition is we appreciate proofs, right? I mean, why do we math? Because it feels so good when we see a nice proof.
Yep.
And I think what we should really try to build is something that can reliably, for a nice proof, say, ah, what a nice proof.
Yeah.
Right? I think conjecturing people have worked on, but appreciation is not something people have done. And so maybe that's something you can come back for the Malinka kick out in a couple of the years.
Yeah, I'd be very happy of that. So indeed, there is this part. I will probably even add a fourth one, which is that in math we're also looking a lot at examples to get an idea. I feel like conjecturing and looking at the examples are a little bit like the two first parts of this talk, but they are always on very specific problems, because having a generic way of conjecturing is something people have worked on, but is, I think, much harder than the proving part. And I think this answers why we've been concentrating on the proving part. It was we had an idea of how to do. That's essentially it. But I completely agree with this comment.
The appreciation thing would be a filter
Yeah.
that kind of, at least a filter that we're using, and that's kind of the most important part
Yeah.
of the reviews we write.
That's
Like,
true.
This is nice, or this is important, or this will have an impact. Then truth isn't even that important anymore.
Yeah.
But these are the hard questions.
I completely agree. But there's one thing. So at the very beginning, we wanted to generate a lot of theorems and filter out the most interesting and the most interesting proofs. And it turned out that we tried to have many heuristics, to have many criteria, and to have many things to try to check automatically these things. And all the time, the model was able to produce something that was completely crap, but that was still passing the criterion. So we ended up, giving up. But it's a very interesting and I think hard question.
Oh, okay. Thanks for the talk. I was, if I get correctly, I mean, the story about getting intuition, for example, for the Lyapunov function, was a large language model which was fine-tuned with this backward.
It was a language model, but not large, and it was trained from scratch.
Okay. So my question is, when I think about things like that, I think also that when I do math, I see things much more than syntactically manage them with a language model, like a language model do. I don't know if that's something that makes sense, but if I write a tangent space or if I write a sheaf or whatever,
Yeah.
I see that more. And also if I manipulate some equations. So I'm wondering if there's some research, if nowadays it is possible to do some research with visual language models, which are trained with the pictures and also with picture of equations, because,
okay, for pictures of equations, I'm not 100% sure it will change much, because what you're giving to the language model is precisely an equation. So whether it's exactly in picture, or the model is going to take this list of tokens and try to create an embedding. And so if you give a picture, it's going to take the picture and create an embedding. But I think there's a close bijection between the two, just for the equations. Now, I feel like the models is essentially trying to do like us, or close in what you're saying, which is that, I don't know for you, but when I see the things, indeed I see them and I have kind of the image in my head, but there's a kind of internal representation that we have of the objects, especially the abstract objects. And I think this is more or less what the transformer is trying to reproduce with the embedding of the object. Some people have tried to interpret what is the transformer seeing behind. So we tried for the Lyapunov function. It was an absolute nightmare. I don't know, saying that the most important thing was the 5 of the x5 is, okay, it's maybe true, but it didn't give me any at least it didn't give me any intuition. But there are people who definitely try to do this on other problems, to try to interpret a bit these. What is hard is that the representation, how the transformer sees the representation of the mathematical object, is essentially a manifold in a space of dimension at least 256. And so it's if you want to see it as a human, you need to project it, and as long as you're projecting it, you need to find the right projection. So I think it's a hard task.
Thanks.
Oh, sorry.
Yes, thank you very much indeed for the expose. There are a couple of questions. The first one, it's towards that system where you scaffold and then you do lemmas. It makes one think that something agentic with retrieval capacities could potentially be useful, but also because mathematics texts are hard, maybe that's a really bad step. So could you say anything about the RAG-like techniques in the...
So I think in any case, having hierarchical techniques is useful. So having a retriever could be useful as well, and especially if you have a good retrieval. What is nice, what is important here is that both are trained essentially at the same time. So that you don't really train them separately, so they get different signals, but they are trained essentially at the same time on different problems. I think this helps rather than training them separately and rather than just a pure agent approach.
Okay, I see. So the second thing, it's kind of about the remark of appreciation. Myself, since I code a lot using the agents, I'm actually very pessimist on the fact where it's going to go if the formalization happens successfully, because the code bases are exploding as we speak, as you know quite well.
Yeah.
And there is a notion of dead text that humanity produces, which I think will only be read by machines. If we continue like that, I don't know what's going to happen. But my question is rather this, okay, so for the few things that we can appreciate, something that was not mentioned is the definitions, or like could we expect AI to create something like category theory, or I don't know, mathematics that never existed a few years back, or I don't know, liquid vector spaces, whatever that was.
That's a tough question. Of course, coming up with definition is I would say formalizing definition is harder than formalizing statement, and coming up with definition is more complicated than formalizing definitions. I think if you asked me 3 years ago, I would have answered, oh, absolutely not. This is not going to be something possible. Now I'm pretty convinced that the answer is yes, but it's extremely subjective. So it's probably because I've been talking too much to Christian Zegedi last week. Merci.
Thank you. Can you hear me?
Yes.
Okay, thank you for the great talk. Following up on this appreciation theme, you mentioned that earlier you tried to apply some heuristics to try to kind of weed out uninteresting insights from interesting insights, and none of those heuristics worked. I wondered if you could just share a little bit about like the heuristics that you thought might work that didn't work, and also what you would try now if you had more time to sink into it.
Okay, yeah. So the first thing before I reclude as myself is that at the very beginning, the theorems that we were generating, because this was 2020, we were trying already to see if we could get something with just inequations, inequalities, and this kind of thing. And the question is, you're proving an identity or you're proving an inequality. What kind of equation or equality could be interesting? And we started with very basic criterion. For instance, you're going from point A to point B. It's interesting if point B really doesn't look like point A, so not too large in length because you don't want something that just puts square root of square of square root of square and so on. But at least you can't get the same patterns. You don't get the same type of operators and so on. And this was a disaster. Like we always ended up having something that was completely trivial. Then we decided to take a step back and say, okay, now we're going to generate theorems. And a theorem is interesting if, so looking at MATLib, we're going to say a theorem is interesting if it's called rarely. So let's say differently. If a theorem is called rarely in the proof of other theorems, it might mean that in the proof of the theorem that it's called, it's probably a key step to try to identify key steps and try to filter out. This wasn't as successful as I expected, most likely because of the structure of these libraries where you have a lot of lemmas that are used only once. And so, of course, there are keys for the theorem that are proving, but there's essentially half the theorem. What did we try? What else did you try? We tried a few other things that I wouldn't remember exactly clearly, but I probably have the list somewhere. This wasn't. This was really purely heuristic, and because it wasn't going anywhere, we stopped. There is definitely space to have a much larger reflection about this and more serious work about this.
Okay, so last question. Yes.
Okay, thank you. I think actually a lesson of, say, machine learning, even artificial, not only in mathematics, is that what you call intuition in this context, right? It has 100 different meanings, but that's capacity to have a good guess without clear foundations, right? It's kind of rather primitive cognitive function, right? So it's a model with machine. But actually, I have doubt how far mathematics can go just with that, because you mentioned the problem of like lacking data, right? It's if we would have more data, we would. But of course, if you think, say, historically, something like in 17th century on algebra, where people tried to solve quintic, like quadric, right? They have general formula that. It wouldn't help, right? They would never invent the Galois theory just by that kind of learning from examples and capacity to give some guesses, just something very different. And finally, you say mathematics is a game. Again, of course, mathematics is what it wants to be, right? It's a social thing. And I think that aspect of game, say, kind of, it's unfortunately in the education, and particularly in that country, I think it very much comes, right, with this training of passing tests, maybe Olympiad, not much better in that respect. But I think that mathematics is really much more than that. But open question is that if we do that you suggest whether it would, help us to open to different kind of mathematics. So we'll see that can computer do it, we humans can, to do something more, or there is probably a danger that we really believe that computer is like a game and we have nothing, which is also possible socially, of course, possible, why not? We may infinitely just solve, some tests and that's it.
So, okay, that's a very interesting question. So I'll first start by saying I don't think we can make it, at least getting a human level and so on, without reinforcement learning. So I'm saying games, of course, but what I really meant here was just having something that where you have a validation that could tell you this is correct or this is incorrect automatically, and this is why we're working in informal language. The reason why there was this focus on Olympiads and all these problems is, I think, half for a good reason, which was that the models at the time were completely unable to do anything else because they weren't good enough, and half for a bad reason, which is that this subject has been a lot investigated by computer scientists more than mathematicians. And if you want to sell something to the machine learning community, you unfortunately need problems that the machine learning community as a whole will understand. And so usually you stop at Bayes-Level at best. So I really don't think this was a really good focus from the community, but everyone was doing this. Now people start to move. The first benchmark that I showed was also a direction, an incentive to try to go in this direction. But I think we're far from being the only one. I think that now that everyone was obsessed with the International Mathematical Olympiads, now that some models got a gold medal, I feel like I'm maybe too optimistic in saying this, but I think people are going to move from this to actually research problems. Now, is it possible that at the end of the day, this kind of with reinforcement learning, at least, this could reach human level performances, and what could we do afterwards? Well, again, maybe I'm very optimistic or too optimistic, but I feel like there has been a pressure to publish a lot in any fields of science, maybe slightly less in mathematics, but still, at least in applied mathematics, I've seen it a lot. And there are, maybe if you have an AI that is able to write a paper as good as some medium-level paper, maybe people are going to focus more on harder problems and take more time to think and get more interested and so on. At least, okay. I'm sure people think that I'm super optimistic about that. I'll try to forget the fact that if you look at the number of papers submitted on arXiv these last years, we essentially get something like this. Yeah, I think that's my answer.
Okay, so I think we can thank you, Amaury, yes.